Boeing's Starliner has faced over a decade of delays, from timing errors that missed the ISS to corroded valves that grounded launches. But these aren't isolated incidents. There's a pattern here that reveals something troubling about how aerospace testing works. Today, we'll trace the chain of failures that show exactly what's going wrong. Boeing's Starliner problems aren't random glitches. They form a troubling pattern that reveals fundamental issues in aerospace development. Let's dissect exactly what went wrong and why it matters. The December 2019 mission failure exposed the most revealing problem. Starliner's internal mission clock was set incorrectly, causing the spacecraft to fire its engines at the wrong moment and burn too much fuel to reach the International Space Station. Think of it like a GPS that's running 11 hours fast. Every navigation decision becomes catastrophically wrong. But here's what few people realize. NASA discovered a second software error lurking in the system that could have caused spacecraft components to collide during re-entry. This wasn't caught until after the failed mission, revealing a deeper issue with Boeing's testing methodology. The root cause? Boeing tested systems in isolated segments rather than running complete end-to-end mission simulations. It's like testing a car by checking the engine, brakes, and steering separately, but never actually driving it. Critical timing and communication problems slipped through because the systems never interacted under realistic conditions. NASA's post-flight investigation required Boeing to implement dozens of changes to their testing protocols, a process that consumed years and became the primary driver of Starliner's schedule delays. And here's what's truly noteworthy. While software dominated the headlines, mechanical failures proved equally persistent. The parachute system, literally the last line of defense for crew survival, suffered multiple critical failures. In 2019, during a crucial pad abort test, one of 3 parachutes failed to deploy due to an incorrectly attached pin. For NASA, this wasn't just human error. It signaled that quality control processes weren't catching life-threatening mistakes before critical tests. 2 years later, engineers discovered that fabric components called soft links, which connect parachute lines to the capsule, didn't meet safety margins for crew missions. Boeing had to completely redesign these components and restart testing cycles, but the mechanical problems extended beyond parachutes. In August 2021, 13 valves in Starliner's propulsion system refused to open during launch countdown. The culprit? Moisture had infiltrated the valves while the spacecraft sat on the ground, mixing with oxidizer to form nitric acid that corroded internal components. This failure highlighted a fundamental design vulnerability. Earth's environment was damaging spacecraft systems before they even reached space. Boeing had to develop entirely new inspection methods and consider design modifications to prevent future occurrences. When Starliner finally reached orbit in May 2022, 2 maneuvering thrusters shut down prematurely due to chamber pressure drops. While backup systems completed the mission, this thruster instability raised serious concerns about emergency maneuver capabilities, critical for avoiding space debris or executing rapid ISS departures. But this is just the beginning. What's really surprising is how these individual failures connect to a larger industry transformation that's reshaping commercial spaceflight. Boeing's struggles with Starliner have fundamentally altered NASA's approach to commercial crew transportation, creating ripple effects throughout the entire space industry. When NASA awarded both Boeing and SpaceX commercial crew program contracts in 2014, the agency deliberately chose 2 providers to ensure redundancy. Boeing received $4.2 billion compared to SpaceX's $2.6 billion, reflecting confidence in the aerospace giant's established track record with government contracts. Yet SpaceX's Crew Dragon completed its first crewed mission in May 2020, while Starliner didn't fly astronauts until June 2024, and even then, the mission ended with crew returning on a SpaceX vehicle. This 4-year gap forced NASA into an uncomfortable dependency on a single commercial provider. The strategic implications extend far beyond NASA's immediate needs. Boeing's delays have strengthened SpaceX's position in the commercial space market, allowing them to capture additional contracts and establish operational rhythms that compound their competitive advantages. Consider the economic ripple effects. Every Starliner delay cost NASA approximately $90 million per seat on Russian Soyuz flights. Before SpaceX, alternatives became available. More significantly, these delays have constrained International Space Station crew rotation schedules, limiting research capacity and operational flexibility. And here's what most people overlook. Starliner's problems have accelerated NASA's shift toward fixed-price contracting models. Traditional cost-plus contracts, where contractors are reimbursed for expenses plus profit, created incentives for extended development timelines. Starliner's overruns demonstrated the risks of this approach, pushing NASA towards SpaceX's fixed-price model for future programs. The broader space industry has taken notice. Private investors increasingly favor companies demonstrating rapid iteration and cost control, SpaceX's approach, over traditional aerospace development cycles. This shift affects funding availability for established contractors pursuing government work. Boeing's challenges have also influenced international partnerships. European Space Agency officials have expressed concerns about relying solely on American commercial providers, accelerating development of independent crew transportation capabilities. Russia and China have similarly emphasized domestic space transportation as strategic priorities. But there's a detail most people overlook about the competitive dynamics. Boeing's struggles aren't necessarily permanent disadvantages. The company's experience with Starliner problems has generated valuable lessons about modern spacecraft development, potentially positioning them for stronger performance on future programs. The timeline significance extends to NASA's Artemis Moon program, where reliable crew transportation systems become critical for lunar mission success. Starliner's delays have compressed development schedules for moon-related systems, creating cascade effects throughout NASA's exploration timeline. And this leads to a remarkable discovery. Rather than simply falling behind, Boeing's Starliner experience is driving fundamental changes in how the aerospace industry approaches risk, testing, and quality control. And here's why this changes everything. The lessons from Starliner's development challenges are reshaping the entire framework for future space exploration programs. The Starliner saga isn't just about one spacecraft's troubled development. It's fundamentally changing how America approaches space exploration and commercial partnerships. NASA's response to Starliner's problems has already influenced the agency's approach to future programs. The Artemis lunar program incorporates more rigorous milestone reviews and testing requirements directly inspired by lessons learned from Boeing's development challenges. But there's a fascinating paradox emerging. While Starliner's delays created immediate problems, they may ultimately strengthen American space capabilities. NASA now has extensive experience managing complex commercial partnerships under pressure, knowledge that proves invaluable as the agency expands commercial relationships to lunar and Mars exploration. The economic implications extend beyond NASA's budget. Boeing's Starliner overruns have cost the company over $1.5 billion in charges, demonstrating the financial risks of fixed-price government contracting. This reality is forcing traditional aerospace contractors to fundamentally restructure their development processes and risk management approaches. Why would Boeing accept this risk? The answer lies in the long-term commercial space market potential. Successfully operating crew transportation systems positions companies for lucrative contracts supporting private space stations, lunar bases, and eventually Mars missions. The current losses represent investments in future market dominance. And here's what's truly noteworthy about the timeline ahead. Starliner's problems may actually accelerate American space exploration by forcing diversification of capabilities. NASA is now actively supporting multiple commercial space station developers, crew transportation providers, and lunar landing system contractors, reducing dependence on any single company. What happens if Starliner succeeds in upcoming missions? A functioning Boeing crew vehicle would restore NASA's desired redundancy, reducing costs through competition and providing crucial backup capabilities for space station operations and future exploration missions. But there's a detail most people overlook. Starliner's development challenges have created unexpected opportunities for smaller aerospace companies. As NASA seeks alternatives to traditional contractors, startups and mid-sized companies are winning contracts previously reserved for aerospace giants. The international competitive landscape is also shifting. European, Chinese, and private space companies are studying Starliner's problems to avoid similar mistakes in their own crew vehicle development programs. This creates a knowledge transfer effect that could accelerate global space transportation capabilities. Yet significant uncertainties remain. Boeing must still demonstrate that Starliner can complete routine crew missions without major technical surprises. The company's recent discovery of fresh thruster problems in early 2025 shows that development challenges persist even after years of fixes and improvements. The broader question facing the space industry is whether traditional aerospace development approaches can adapt quickly enough to compete with newer companies using rapid iteration methodologies. Starliner's experience suggests that fundamental cultural and process changes may be necessary for established contractors to remain competitive. Looking ahead, success metrics for Starliner have evolved beyond simply reaching operational status. The spacecraft must now demonstrate cost-competitive operations, reliable performance, and the ability to support NASA's expanding space exploration goals. But here's the ultimate irony. If Boeing successfully resolves Starliner's remaining issues, the spacecraft could become one of the most thoroughly tested and reliable crew vehicles ever developed. Every failure has driven improvements that may ultimately create superior safety and performance characteristics. The stakes couldn't be higher. America's space exploration ambitions, from permanent lunar bases to Mars missions, depend on having multiple reliable crew transportation systems. Starliner's success or failure will determine whether the United States maintains the redundancy necessary for sustained space exploration leadership. And that's why Boeing's next Starliner mission isn't just another test flight. It's a crucial moment that will shape the future of American space exploration for decades to come. This is exactly why Boeing's testing failures matter far beyond one spacecraft's troubled journey. What NASA engineers discovered through Starliner's problems has fundamentally changed how America builds systems for human spaceflight, creating stricter standards that will make every future mission safer. The bigger picture? We're witnessing the transformation of an entire industry. The lessons learned from Starliner's decade of delays are now embedded in Artemis lunar programs, Mars mission planning, and the next generation of commercial space stations. Every failure has strengthened the foundation for humanity's greatest exploration goals. And this is just the beginning. Boeing's upcoming crew mission will either validate their new testing approach or trigger another wave of industry-wide changes. Meanwhile, 3 new commercial space stations are entering development, each incorporating Starliner's hard-won lessons. How do you think Boeing's experience will influence the next decade of space exploration? Will traditional aerospace finally match the rapid innovation we've seen from newer companies? This is Space Hub, and we dive deep into the engineering decisions shaping our future beyond Earth. For more analysis on what's really driving space exploration forward, you know where to find us. The path to the stars has always been built on learning from setbacks, and Starliner's struggles might just be paving the way for humanity's most ambitious journeys yet. After 21 years in development, Dreamchaser's 26 rocket engines still can't solve its fundamental problem. While SpaceX delivers cargo routinely, this winged spacecraft remains grounded despite billions in funding. But here's what most people don't realize about why wings and precision engines aren't enough. Today, we're revealing the real engineering trap that's keeping Dreamchaser earthbound. Dreamchaser's 26-engine propulsion system represents the most sophisticated spacecraft maneuvering technology ever built for cargo delivery. Each engine can fire at 3 different thrust levels, high, medium, and low, creating what Sierra Space calls surgical precision for delicate operations around the International Space Station. Think of it like having 26 individual steering wheels on a Formula One car, each with 3 different sensitivity settings, all working together to thread a needle at 17,500 miles per hour. But here's what few people realize about this engineering marvel. Those 26 engines are actually trying to solve a problem that SpaceX's Dragon capsule doesn't even have. When you choose wings over a simple capsule design, you inherit a cascade of complexity that no amount of engines can fix. The propulsion chemistry alone reveals the scope of this challenge. While SpaceX's Dragon uses traditional hypergolic fuels, chemicals so toxic that ground crews need full hazmat suits just to approach the spacecraft, Dreamchaser runs on what seems like a revolutionary green propellant system, kerosene and hydrogen peroxide. Sounds environmentally friendly, right? Ground crews can literally walk up to Dreamchaser in regular clothes after landing. However, this seemingly brilliant choice created an unexpected engineering nightmare that's been plaguing the project for years. Hydrogen peroxide isn't just corrosive to most metals. It naturally decomposes into water and oxygen over time, essentially eating away at your spacecraft's fuel lines during extended missions. We're talking about a chemical reaction that could literally dissolve critical components while Dreamchaser sits docked to the ISS for months. Sierra Space's solution showcases both their engineering brilliance and the depth of their problem. They turned to zirconium, one of the few metals that both resists hydrogen peroxide corrosion and doesn't accelerate its decomposition through ionic reactions. But sourcing, machining, and certifying zirconium components for spaceflight? That's not a 6-month engineering task. It's a multi-year material science project. And here's what's truly staggering about the specifications. Dreamchaser can theoretically carry 27,500 kilograms to low Earth orbit using ULA's Vulcan rocket. That's roughly equivalent to lifting 15 cars into space simultaneously. The 15-foot cargo module was specifically engineered to maximize Vulcan's lift capacity while maintaining the precise aerodynamic properties needed for runway landings. But theoretical capacity means nothing if you can't get the certification to fly. The timeline reality exposes the magnitude of this complexity trap. SpaceX's Dragon took just 4 to 5 years from NASA contract signature in 2006 to its first flight in 2010. Dreamchaser? We're looking at over 2 decades. The project started as a concept in 2004, merged with Sierra Nevada Corporation in 2008, received its first NASA funding in 2010, and here we are in 2025, still grounded. According to NASA's ISS program manager Dana Weigel, the current bottlenecks center on 2 critical areas: software certification and propulsion system validation. Every single line of code must be tested end-to-end to ensure perfect operation in space's harsh environment. But the